it goes better. Okay, so open up your notes, and we're just going to do the boiling. So the first one, property, we're going to skip the first two and go down to the property about boiling, okay? So that's the demo we're going to look at first here. Okay? So first thing with each of our properties, Sophie, did I hit play? I always forget, I said it in there. So the first thing is you do need to understand the definition, right? Because you need to understand what the property is in order to then connect it to IMFs, okay? So boiling point, this one actually feels like you probably know what it is, but you actually may not in terms of a chemical understanding. Because most people think of boiling as they think of bubbling water, cooking mac and cheese, right? Hot on the stove, that's boiling. Which, it is the boiling process, but boiling isn't so much about what temperature it's at, it's about pressure. And it's about that there's pressure that pushes down on a liquid. It's called the atmospheric pressure we live in, right? There's pressure pushing down. In order for a substance to boil, the molecules down here have to be at the same pressure, which pressure is a measure of like force, to be able to break the pressure pushing down. So boiling point is the point at which the pressure down and the pressure up are equal, and so now the bubbles can escape. Now, where temperature comes into play is temperature gives the molecule more force. And so that helps in the idea of giving it enough force to break through. But what's different is another way you can get things to boil is by removing the pressure. Things boil quicker when there's less pressure pushing down. Hence in Utah, water doesn't boil at 100 degrees. It boils at 98 degrees because we have less air pressure because we're at a higher elevation. On Mount Everest, water boils at like 72 degrees because there's less pressure up there. In outer space, water boils instantly.
Wait, if you just took water out there?
I mean, you have to throw it out of a spaceship, yes. But yeah. So next time, this was one demo. I'm so sorry, I forgot to set it up, and I don't have, it takes a little bit, but I'll do it next time. I have a vacuum chamber where there I can take out all the pressure, and we can get a beaker of water just to boil. But then I can literally take the beaker out and drink it, because it's not hot. So boiling isn't about it being hot, it's just having enough energy to overcome the forces pushing down. Does that make sense? Now keep in mind, if I were to boil water on Mount Everest, it's boiling sooner, because it boils at 72. Is it going to cook my noodles faster? No, it's actually going to cook them slower because the water's not as hot, right? So cooking is about having the heat, and that's once again how an Instapot or a pressure cooker works.
So if you took a vacuum, if you were trying to boil something on an airplane, would it boil what temperature?
Well, it's pressurized.
That's the difference though, is they pressurize the airplane. But if it's depressurized, then you can boil it quite quickly. But then you also have to have the oxygen mask that pops out, right? But yeah, good thinking though, right? Okay, so I'm going to walk through this first one once again as kind of a model of how we're going to think through this, and then with each demo, it's going to get like more on you guys trying to figure it out. Okay? So the connection we're going to make here, and my sentence disappeared, but yours is fine on your paper. Yours says something along the lines of, we skip over to the section, it says the blank, the intermolecular attraction, so write the word stronger. Okay, so this is where we're trying to make the connection between the two. So the stronger the intermolecular attractions, here's how my brain thinks about it, because we want to connect to the IMFs. If something has strong IMFs, I imagine the water molecules linking arms tightly. So if something has strong IMFs, if I want them to boil, it's going to take more heat to do so. So the higher the IMFs, the higher the boiling point. So your second blank would be higher. Okay, I left these blanks up here on purpose because as we go through these properties, it's something I want you guys to be thinking about, what is that connection? Okay? Okay, and then the final piece is, to bring it to life, we'll do a little demo with each of the properties to make claims about them. Okay? Now once again, this one's been done for you on this white paper, but it'll kind of give you a model of what I want you to do. Okay? So the demonstration is, and I'll pass them around, is I have these little fun-looking, I don't know, flasks, there's the words. Okay? They're different colors just for fun and different shapes for fun, and it has nothing to do with, like, the liquid. It's all the same substance. They just dyed them. Okay? So, I'll pass them around so you can try it for yourself. Don't do that. Okay? But this is known as a hand boiler. If I hold it at the bottom, and I'm not a zombie, I can actually get it to boil. Okay? So if you look over in the far column, our claim evidence reasoning would be that the liquid in here must have very weak intermolecular forces due to the fact that it didn't take much energy to get it to boil.
So do they just reduce the pressure inside of it?
There is also a pressure component as well. The liquid itself does boil quite easily, but they've also created somewhat of a vacuum chamber. Yeah. Okay? So that's why if I let go, the pressure difference is what causes it to kind of like stay up there. So then just grab the top and you can get it going. Now, if you're a zombie, it won't work. So, meaning your hands are cold. So if it doesn't work for you, I'm going to tell you. Or if you have cold hands, start rubbing them together. So I'll just give one to each row, and then you can kind of like try it and then pass it down so everyone can try it. They obviously are glass, so be cautious as you pass it.
Are they different?
They're the same.
No, they're the same. They just made them different colors.
Wait, are we putting that right here?
Go ahead and try it, and then pass it down to your neighbor. And then experience the joy of it.
We're a vampire. I guess would it work for a vampire? Exactly. Yeah, you can be a vampire then.
A vampire? Oh yeah, that's true. Someone be a vampire. Or my other, an AI robot.
Robot, yeah.
Right, they probably don't generate heat.
I guess it would depend on the alien though. Some of them would produce heat probably.
It's interesting to see, yeah, like some it goes so fast forward, and then others it's like very slow.
Since you're too cold, it won't be.
If you have always cold and uncold, would it just like boil right in the middle?
Yeah, it kind of just like, well, it depends. Like your hands or one of each hand, because then it kind of goes to which one is like. You get it's like a battle, right? Like whichever is water pushes it.
Wait, hers was so
the
good.
other way, yeah.
What
I have warm hands. I have really good circulation. Oh, it's so slow.
Like
Alright, can I pass it over this?
so fast. That's a lie. I get cold really easy sometimes, and then other times I guess it just changes temperatures very easily. But I do. Oh wow, it's taken forever. Yeah, maybe don't throw it.
Yes, Alex.
So wait, how does it push off?
Yeah, so have you, like, you can hear, like, the sound while it's, like, warming up and then it stops?
Yeah.
It's like when you hit start, you can initially hear air being pulled out.
He's a vampire.
So it's pulling air, no, wait, it's pulling air
And he's a vampire.
in. No, out. Yeah, so it's putting air into it because it wants a higher pressure because then it actually makes the water have to boil at like, because normally you can't get water above 100 because it just turns to a gas. But if you apply pressure, you now can get water to be like 150. So now it's like, it's cooking at a much higher temperature. And that's why when you then release it, it's like all the extra air is coming out. But that steam is like crazy dangerous because of like how hot it is. So it's like the opposite of a vacuum chamber, pressurized chamber. Yeah, it's not gonna cook it any faster. All right, we're passing it.
Oh, I got it. We're both like half
You're half
vampires.
vampires. Oh, and it's so slow.
Oh, there it goes, there
There we go.
Okay, keep passing it down the row so everyone can get a chance. Question, Jack?
I feel like decent yeah, like
So there's in order for it to become a gas, it has energy to break that pressure. And so like temperature helps in that, but it's really about the pressure. Okay, pass it down to John, give him a turn.
An A relay and an A.
Jack, go get us the thing.
We could close. So I mean, yes, some of it is but then because it's a closed system, like
Next thing that I magic.
Jack, you're about to set the place on fire. You guys should pass the... We're warming up.
Why are you doing faster than stable than it did with me? How cool, man. Oh, it's going.
Things are cool.
Apparently I'm looking at their cars. Why does it faster than wind?
Why are my hands just freezing?
If a vampire rubs their hands together when it's so
Why are my hands just so
yeah, and like they probably think it's for temperature otherwise. And then if they got it in the beam,
okay.
they'd be slightly over temperature. If a vampire rubs their hands together on the blood.
Alright, we're in our last two.
Hold on, Jamie.
We can have races at the end.
High five.
We're both dead.
Thank you. Okay, so then the last piece is, once again, now connecting it to the symbolic side with IMF. So the question here says, which would you predict to have the highest boiling point? So the connection we established was, the more IMFs, the higher the boiling point. So which one has more IMFs? And these should look familiar from our quiz. Yeah, so circle water, right? More IMFs, higher the boiling point. Okay, so we're going to repeat this pattern for different properties, but keep that perspective in mind of where we're trying to get, right? Of connecting the IMF to the symbolic of what it all connects. Okay? Alright, so the next property, we'll go back to the top of the chart now, is surface tension. Okay? So surface tension is the energy required to increase the surface area of a liquid by a unit amount. Sounds kind of fancy. The basic idea, once again, is it's just, read the word backwards, the tension at the surface. Right? So when you have a liquid substance, the molecules, because of IMFs, grab onto each other. Okay? So, don't say it out loud, but you can whisper with your neighbor. So what would our connection be? If something had strong IMFs, the stronger the IMFs, the what the surface tension? What would be, just write it down, so what would be the connection there? If something has strong IMFs, what could you claim about its surface tension? You can whisper with your neighbor. Okay, point with your finger, saying I think stronger IMFs mean stronger surface tension or weaker surface tension. Point up or down for me. Is it a direct relationship or what we call an indirect relationship? Very good. If you're pointing up, have a smile. And you don't have them because you turn them in, just write it down somewhere and then you can add to it. Sorry, I haven't got it written down. Okay? So then, which one would you predict to have the highest surface tension? H2O, right? More IMS means more surface tension. Okay? Alright, demonstration number 2. Okay? So write number 2 on your white paper. Okay? The first box box is just for your observations. The second one is, keep in mind, I'm not telling you to, like, you don't have to exactly explain everything you're seeing. Your job is just to make a claim about the IMFs of the substance. Now, with some of these demos, you're going to know what the substance is because it's part of me setting it up. Okay? But keep in mind that I want your evidence to be based on what you observed. Okay, so based on your observations, what can you claim about the IMFs of this substance? Okay, so your first statement should be just like the one there of the liquid has what type of IMFs, and then justify it based on what you observed. Okay? All right, now if you've seen any of these demonstrations before, I ask that you don't, it's like a magic show, don't give it away until I tell you it's time to give it away. Okay? Don't ruin it for people. You're like, oh, I know why that's working. Okay? Let them have the chance to be amazed and think about it, okay? All right, so I'm going to be using water. So water is what we're going to make a claim about, which, once again, I know you already know what its forces are, but make your evidence based on what you're seeing, okay? I have it's one of our little pass-out cards, just using a laminated piece of paper, okay? And then I have a mason jar, okay? I'm going to fill it up here with about halfway full of water, okay? I'm going to take the card and put it on the lid of our jar, like so. Okay, and then I'm going to take away the card. Are you ready?
Stay up.
Oh, whoa.
Whoa, whoa.
There you go.
Okay.
All right, so make me a claim based on what you saw. Obviously, it links to surface tension, so you can put that in there as well. Okay, make a claim based on its IMFs and surface tension. You can talk to your neighbor about this one. The next one I'm going to have you try without your neighbor, but this one, if you want to brainstorm with them, you can. Okay, I'll give you 2 minutes. Come up with something for me, okay? But you don't explain what you saw, but just what can you make about its IMFs. And it cannot be, I claim this out because of the water measure. It's cool as that would be, but that is what I probably think. Yeah, I can see that. I can see that actually. You'd be fired.
You look like a waterbender. I mean, you could give up a little bit of water.
Yeah. I feel like that's what I resonate with the most.
I missed the opportunity 4 years ago.
Oh, I understand that.
Because it's disturbed, so then it's
Lindsay, give me something. I'd rather have you write down something that's wrong, but you're trying to think it through. This is how you learn how to problem solve, is by just trying. Try to problem solve even if it's wrong. Once again, your key things I'm looking for in your answer are a claim about the IMFs, and then evidence based on what you observed. Okay. Front row, turn to your backdoor neighbor and share with each other a row. Third row, turn to your backdoor neighbor, share with each other a row. If you don't have someone directly there, make like a threesome. So Bryson, you get 2 buddies.
I said
John, you can just destroy this.
Yeah, that's right. I'll be your answer. That's why I didn't get it.
That, yeah.
if you honestly tried your best in answering something down, you can have a smiley face for trying. I would like to hear from 3 people. If you could just read for us what you wrote, just to hear it out loud, some different ways of our claims. Anyone willing to share for some more smileys? Alex, let's hear one.
So I said the liquid has high intermolecular forces. The water held together, which didn't allow air to get past it, and that held it up, and that's a result of high IMFs.
Love that. Very well said. Have a smiley face for that. Someone else. All you have to do is read your paper. Right.
I said the water must have had strong IMFs because the surface tension must have been stronger in order for the water to stay in, and if it has high surface tension, then the IMF will be stronger.
Love that. I love your last part of like the connection back. Like if this was happened, then this must be true. Right? Like that's how I problem solve all the time. Is I say, well, if this happened, this has to be true, right? Because it's the connection. No, good. How's my face flat? One more. Bryson.
I mean, me and Alex worked together, sort of, but I said the liquid has high intermolecular forces, and I said this is seen in the water floating and flipped upside down, and I said this is because the hold of the H2O molecules is super strong, so the IMF is super strong.
Love that. That the H2Os must be holding strong, hence the IMF is strong too. Good. How was my face that? Thank you. All right. Now this obviously, if you try this trick at home, it's not gonna work because there's obviously a trick behind it. Water does have very high IMFs, but it's not that high to overcome gravity completely, right? So I have altered my jar slightly. There's a window screen glued to the front of it. I told you it was like a magic trick of painting reality. It is still pretty cool to think, like, there are still holes, right? Right? It still can come out, but the forces are strong enough that those little waters can hold on to each other and the net. And if you think of the size of a water, like those holes are tiny to us, but how many water molecules are actually across a hole? I should figure this out one day. Like billions, right? So imagine like a billion long rope of people holding up to each other over a cliff. That's what the water is doing. That's
That'd be
pretty
kind of
amazing.
cool. We should try it.
We should do it ourselves. The one question I really do want to try that I need to test over these years is at what point does gravity win? Like how big of jar can I do? And it doesn't come out? Was that online or in person? I question the legitimacy of
You should
that.
try it with putting a water bottle.
I don't think I think a hole in the water bottle is still too big. Should we grab one?
Ben
Yes.
has a great way of describing this.
Yeah.
Totally
Let's see. Okay.
Oh my gosh.
No! No way!
Yeah.
I've never seen Lego Batman. But it sounds like a really good analogy. So now I might need to overcome break. Go watch Lego Batman. Because I can visualize what you're seeing there. But, Ben, have a smiley face for your awesome analogy. Okay. I think they lied to you on TikTok, right? I don't think this will work. Or whatever. I don't know. I just assumed you saw it on some sort of like video reel type thing, right? So they did this. Like that?
Yeah, but it was like,
Yeah, it's
I don't know, very like,
It's gonna make a big mess.
yeah. I don't think it's
Was there not much water in there? Should I empty some water out? Probably.
I don't know. I
Just
don't
put like
I
one
just
drop.
feel
That's
like-
some good drinking water, man.
I would have loved to drink that.
Alright, 1, 2, 3.
Okay. Wait, hold up. There's gotta be a drop in
Suck.
But even with the net, what I'm curious is like how big a bucket with a net? Because at some point the gravity's still gonna overcome it, you know? Like, could I hold a bucket over Zach's head and the water doesn't come out? Like, that'd be
I wanna see that.
So,
Yeah, let's try it.
okay. Well, I need a bucket and I need more window screen. And then we can try it. Okay, second property. Let's look at this one. So this property is called vapor pressure. Once again, whenever you have a 2-word definition that you're trying to understand, I always read it backwards, and that seems to help, right? Like, so surface tension, tension of the surface. Vapor pressure, pressure of the vapor, right? That's literally what it is, right? So vapor, by the for something that is normally a liquid, but now it's in its gas phase. So for example, like water, we don't typically actually call water a gas, we call it a vapor, but it's the same thing. It's just, it normally is a liquid, okay? So what water vapor is, we use this water for this bottle for two reasons, okay? Is if I have a closed system, meaning gases can't escape, the vapor pressure explains the amount of gas, the amount of water that has evaporated and is filling the space. Because even when a substance isn't boiling, a certain amount evaporates over time, right? The vapor pressure describes this. How much gas is there in the vapor state, okay? That's kind of, once again, what the picture is showing you. So this, we would say, like, has a higher pressure than, like, in this picture, because there's very little gas in the vapor state, okay? So let's build our connection here. This one I want you to do without talking, okay? So use your own brain here. I'll do the first blink, you do the second. So the stronger the intermolecular forces, the blink, the vapor pressure. So what can you claim about vapor pressure if you know the IMFs are strong? And then try this one on your own too. So circle which one, based off your claim, which one would have a higher vapor pressure. Set your pencil down when you're done thinking. And then we'll share in a second by pointing up or down. But don't do it yet. We'll share in a second. Okay, on the count of 3, you're going to point up if you think it's higher, meaning strong IMFs mean high vapor pressure, or point down if you think strong IMFs mean low vapor pressure. Okay, ready? 1, 2, 3, point! Good. If you're pointing down, have a smiley face. Well done. So once again, IMFs, I visualized Red Rover, right? Molecules holding tight. So if they hold tight, they're not going to evaporate as easily, right? So this one is, we call an inverse relationship, because when one is strong, the other is low, okay? All right, we're gonna do demo number 3. For this demo, I also want you to think on your own. So if some of you did it last time, but this time I want you to think on your own. Let's have it quiet for 2 minutes. Once again, make a claim about the substance, connect it. It's not quite vapor pressure. I couldn't come up with a demo exactly about vapor pressure, but it's about evaporation, which is like linked to vapor pressure, okay? All right, for this demo, you're gonna put your hands in fist and hold them out. I'm gonna come spray you with 2 liquids.
Acid?
Okay. The substance you're gonna make a claim about is the one in the yellow bottle. Okay, this one is water. Okay, but I want you to make a claim about the yellow one. Okay, so on your answer be like, the substance has what type of IMS you're talking about the yellow. Oh, you want to do screen again?
She is a water bender.
A liquid bender?
Ow!
Now I'm ready.
You got water on my paper.
Oh, yeah.
That's crazy.
But now I just have a wet hand.
It was like,
I felt that.
What the heck?
Once again, the pink one's just water. So that one you can like.
Not making my stomach now.
That was so weird.
Okay, no talking. 2 minutes. This is your own time to think. Don't talk to your neighbor. Come up with a claim on what's in my yellow bottle. Not what it is, but what can you claim about its IMFs based off what you observed. I got your papers with the water. Make it look dry, honestly. Are we using butane? Not today. I don't know what purpose it is butane. I guess I don't use butane for that purpose. But that's true. Okay, turn to your table, buddy, and just share with them what you wrote really quick. Ready, go. Okay, let's hear from 3 people. I know it's repetitive, but in learning how to write better FRQs, it's nice to hear the same answer 3 different ways because it can give you ideas of like, oh, I really like how they said that, or like, oh, that vocabulary word made it really clear. And it can help make your answers get better, okay? By the way, everyone have a smiley face. Thank you for keeping it quiet during quiet time. I really appreciate just giving yourself time to think. I know it can be hard, right? But like, I value those moments of just thinking individually. Okay, 3 volunteers, where I'm gonna pick on 3 people to share their answers. Jonah, let's hear it.
The liquid has a weak ion amount. This is because it evaporates very quickly and therefore destroys compounds.
Love that. Have a smiley face. Thank you. Zachary.
The liquid has weak intermolecular forces. The vapor pressure was very high, as evidenced by the quick evaporation. Therefore, the IMFs are weak.
Good. I love that word therefore and like wrapping it back up together. It's always a great way to make sure like you go full circle. Daniel.
The liquid has weak IMFs since it evaporated quickly as a high vapor pressure, and we can infer it as a weak IMF.
Lovely. Good. Have a smiley face. Levi, you want to do one more?
Because the liquid in the yellow bottle evaporated fast, we can tell that it has low IMFs.
Good. We can tell, right? Like this, if this happened, then this has to be true. Right? Good. Have a smiley face. Fun. Okay. Questions on our first 3 properties. All right, we're going to look at a few example AP questions now of these 3, and then we'll talk about our last 2 properties, okay? All right. Where did this? Where did boiling? Come back here. Oh, coming here really quick, I forgot to mention this with boiling, but I want to point out, so if you were to take ice and measure its temperature constantly as it melts and then as it boils, and actually if you do this for any substance, they always end up with a very similar heating curve where it increases and then plateaus. Increases, plateaus, and then increases. Every substance does this. The reason why, the point at which temperature doesn't actually go up, I'm still putting heat in, right? The oven's still on. But the temperature can't increase because all the energy is being used to break the IMFs. Because temperature is just speed. So if it's going to climb this way, that means the molecules have to move faster. Well, the molecules can't move faster until I've broken all the friendships apart. Right? Like I have to move the molecules away from each other, and then they can start going faster. And then same thing in the process of boiling, you've got to move them apart even further, and then they can move faster. So kind of recognize that that's the reason of the plateau is the breaking of the IMFs, okay? It's also why, like, once again, you can't get water to boil hotter than 98 ever unless you put it in a closed system and change the pressure, because it's always just going to stay there as the IMFs are broken, and then the water will evaporate or boil away. So
Why
yeah,
pressure cookers cook things so
Yep.
fast?
exactly. Yeah. So that's why they're able to get the water. I don't know what temperature they cook at, to be honest. Pretty darn hot. I'll have to look that up. I don't know. Okay, so now here's a question in reverse of what we've seen. So if I tell you that substance A has a higher boiling point than substance B, what can you claim about the substance intermolecular forces? And you can answer about B or A. Try this. So this is back on your note packet, by the way. Sorry, a little bouncing back and forth here. Okay, 60 seconds here. Kind of bringing it together, and then we'll look at an AP question. Okay, and there's a variety of answers, kind of, because you could talk about A or B, but the overall theme should be the same. All right, let's hear from two people who haven't shared yet today for some smiles. What do we put? Yeah, Alex, go ahead.
I said that, like, that means that substance A has higher IMFs than B because this means that it will take more energy to break the bond apart, turn it into a gas, hence like the higher boiling point.
Perfect, because if I know the boiling point is higher, then it's always a valid claim to say those IMFs must be stronger. Even though I have no idea what they are, but they must be stronger if the boiling point, right? Good, have a smiley face. Lily?
I said basically the same thing. I said substance A has stronger IMFs because it is being held together stronger than substance B.
Perfect. Based on the fact that we know their boiling points, right? Good, have a smiley face. Okay, let's take a look at this problem, and I'm going to do, you're going to see Mrs. Alviso or Jamie. This is how, like, my brain would problem solve this. Okay, once again, so this is an AP question, straight from, I remember, I think last year's test even. In this class, if you haven't figured this out already, it's about problem solving. Okay, when I take a test, so I take practice tests, like just to like, you know, when the new test comes out, I take it myself to make sure I'm covering everything I'm supposed to. I have to problem solve it. I can't just read it and be like, oh, I know the answer, because they don't write the test that way. They always write them in a way that make you connect the knowledge you have together. Okay, so there's nothing wrong with you if you're like, why do I have to always think so hard about these questions? It's just the AP test they're making you think. Okay, so you're gonna see I'm gonna talk out loud of like, this is how I would think through this question. Okay, so it says we have 4 different liquid compounds in the flask represented above, A, B, C, and D. Okay, the table, also above, identifies the compounds. So I don't know which is which, but I know there's these 4 things in those 4 containers. Okay, we're focused on flask C, and it shows that most particles are in the vapor phase. Okay, so right there my brain would say like, oh, vapor C has a high vapor pressure. That's what that picture is showing me, okay? This is just like, as I'm reading, I'm kind of like piecing together what I see, okay? The question then says, based on the data table above, okay, make a prediction of which substance is in flask C. So I need to connect the pictures to the table. So my brain says, okay, if something has a high vapor pressure, that means it must have low IMFs. Okay? The table gives me data about boiling points. So if I can connect that to IMFs, then that connects the two together. So the connection between boiling point is, if something has a low boiling point, then it also has low IMFs. It's fine. questions on how we got to the answer from there? Yeah, Ian. Well, Celsius to Fahrenheit is not a clean transition.
Is it like 36 plus?
Say what?
Is it about room temperature then?
It's pretty close to room temperature. Yeah.
Is it like 36 plus like 1.8?
It's so weird. You do like 9/5 times the temperature plus something. I don't know what's wrong with. I know. They should just get
Why don't we
scared.
use Germany?
Because we're America. We needed independence
It's
from all
stupid.
things.
It's stupid because nothing makes sense. It's like the boiling temperature is weird. Everything's weird.
It's dumb.
Is it freezing temperature at Celsius 0?
Yeah. So Celsius 0, 100.
And ours is
Okay,
like-
questions on this one before I have you try one on your own? Okay, try this one. You can talk to your table buddy, but try this one for a smiley face. Would you expect BR2 or BRCL to have a higher boiling point? You don't have to justify this one. Obviously, you should know how you came to the answer, but there is no word justify, which means just tell me which one is higher. Okay, so which one's going to have a higher boiling point? Set your pencil down when you made a choice.
Well, yeah, we have to think about it on the line.
You know? Maybe there's a reason in college my college coach never wanted us to get a boyfriend. So it slowed you down. But then the weird thing was, is it made boys go faster. So girls slowed down when they got a boyfriend. Boys got faster when they got a girlfriend.
My coach always says like 2 months before state you can't break up. So you're stuck with that.
Because otherwise it messes you up. Yeah.
So we need to have really strong friendships and then we'll hold to
Okay, show me number 1 or number 2. Which one's gonna have a higher boiling point? 1 or 2 on your fingers. Okay, you're showing me 2 have a smiley face. It's all about IMFs. And so BRCL is gonna be polar. So it's also gonna have dipole-dipole, so I would assume that it's gonna have a higher boiling point. Okay? Now, I want to point out here, okay, on this question and the question before, I want you to notice that on both of these questions, neither of them said anything about intermolecular forces in the question. The word IMF is not here, the word IMF is not there. Obviously, you're in the unit of IMF, so you're like, oh, I gotta use IMFs. But what we gotta think about is at the end of the year, when all your units are combined, what about these questions should signal to your brain, I need to think about IMFs? Boiling, right? Any question about boiling or really any sort of phase change, think IMFs. Is that what you're gonna say too, Ian? Yeah, good observation. So kind of recognize the connection your brain needs to make, otherwise it can be very confusing. Like I don't even know what to do. But once you realize it's about IMFs, then sometimes the pathway becomes much more clear of how to connect it. Okay? All right, what if though, instead of this question, what if the question said this? The boiling point of BR2 is 332 Kelvin, whereas the boiling point of BRCL is 278 Kelvin. Explain this difference in boiling points in terms of all intermolecular forces present between molecules of each substance. Why is this feel weird?
Because the boiling.
Does this match what we predicted? Oh, no. Right? Based off just the symbols, we would have predicted the other way around. And if this is all that you were given, you're right. I would predict BRCL myself. But if we remember from last time when we compared our charts, there was a little graph that compared the strengths of forces. And I told you to like circle that, right? There's an exception zone. be stronger than some dipole. That's what this is. But the nice thing is they're always going to give you data for it. You don't just have to have known that. Once again, if the question didn't have the data, then I'd assume BRCL. But if the data is given, what does that tell you about their forces?
Higher.
They must be higher, right? If the boiling point is higher, then the London forces of this must be higher than the BRCL. And I wanted you to have it in writing, but here's the example answer of how they justified it. Once again, talking about the forces, but then talking about that, well, since BR2 is so big, right, because remember, London gets stronger the more electrons you have, so that's what this fancy greater polarizability of the electron cloud, right, that just means it has more electrons in there. It allows it to be a stronger force than the combined forces of the other. Okay, so they love, love, love to do this on the AP exam. They love to give you an exception, and you have to justify it. But you don't have to know it without the data being there. Just make sure your answer supports the data. Levi.
What's an electron cloud?
That's just remember this thing? So this is the electron cloud.
Oh.
And remember how with London, the cloud changes shape? So that's what it's referring to as the polarizability. Yes, squashiness. Polarizability is the squashiness of it. That the more it shifts, the more polarizable it is. So yeah, good reminder. Questions on this idea of the exceptions? Okay, let's try one more practice problem, and then we'll probably have time for one more demo, and then we'll finish up the rest next time. Okay? All right, try this one on your own. Okay, so don't talk to your neighbor, try it on your own brain. Okay? So it's telling you that these two molecules have all three forces. They have London, they have dipole, and they have hydrogen bonding. Okay? But the acid, salicylic acid, has a higher, much higher melting point than our methyl does. Your job is to explain why. Why would this one take more than that one? Once again, the question I would ask or what I would always say is okay, well, if that's true, there must be something about salicylic acid that's different than the other one that causes it to hold tighter together. Okay, so see if you can find that difference and write it out real quick. I'll give you 2 minutes. You know they have all three forces, but obviously there's something about methyl where its three forces are stronger. So can you find where that might be? I mean with salicylic acid, right? So maybe think through the three forces. Think about London, think about dipoles, think about hydrogen bonding. What's different about them and why would that make it hold tighter? Okay, try to finish up your answer in the next 10 seconds for me. Once again, the goal with our writing is to make it to the point, explain it well, and then stop. Right? Like on a time test, you don't want to write more just to write more. It won't help you. Right? Learning how to consolidate our answers is another reason why we share out loud, as you can maybe hear how people said the same thing you said, but maybe in a much shorter way. Okay, can I hear from 2 people who haven't shared yet for 2 more smileys? Kenzie, let's hear it.
I said the salicylic acid has a stronger hydrogen bonding force because it has more of those bonds, therefore the melting point is higher than the methyl.
Perfect. So Kenzie hit it right on the head. That it's all about this one has 2 sites to hydrogen bond. Right? So once again, like I said, find the difference. If I look at these structures, the main difference happens up here, where this one goes to this CH3 thing, but this one goes to an OH, which is a site for hydrogen bonding. So this one can hydrogen bond. So I would circle this if you have it. So circle this, circle that. This one has 2 sites for hydrogen bonding, while this one only has 1. And the more sites you have to hydrogen bond, the stronger that force is because it can link in more places. Bryson?
I guess would it also have higher intermolecular forces because there's less atoms that it has to pull on?
Not actually. Because actually, technically, more atoms with, like, if you think of the 3 forces, London gets stronger if you have more electrons. So actually, generally, bigger molecules typically have stronger forces. Does that make sense? But not a bad thing to notice, because you did notice a difference. So thanks for sharing that, Bryson. Jonah, did you have one to add? Oh, okay. All right, questions on this question? All right, that hopefully gives you a little bit of, like, exposure to some, like, what you could see. And like on an FRQ section, obviously we'll do some AP classroom quizzes where you'll see those ones as well. Okay? All right, to end, I'll give you a sneak peek. How about that? But we'll talk more about this when we come back after fall break. The last 2 properties we're gonna look at are solubility and being miscible or not. They really mean the same thing in the fact that solubility is about being able to dissolve. So salt is soluble, wax is not soluble. Right, we did this with like metals, right? Metals are not soluble, but ionics are always soluble. So it's being able to dissolve. It doesn't have to be water to be soluble. You can talk about solubility in a different substance. Normally they would specify that it's a different substance, so if it's not assumed to be water, okay? Miscible is really the same idea, but now it's a liquid to liquid comparison. So you don't really say the liquid dissolved in it, but it's the idea that they mix together. So for example, water and oil are immiscible because they don't mix, but alcohol and water are miscible. If you put them together, you can't see the difference anymore. They make a homogeneous, same mixture throughout. Okay? The idea of this property goes into the fact of similar forces. So now it's not about strength. All the other ones are about strength, right? If this is strong, this is strong. Or if this is strong, this is weak. This one's not about strength. It's about forces with each other. It's the force that the water has in relation to the force that it's mixing with. If the forces are similar, meaning polar and polar, then they'll mix. If the forces are not similar, polar and non-polar, then they don't mix. Okay, so I have a piece of paper, I have 2 pieces of paper, I have water. I'm going to put these paper in the water and we'll observe what happens. Okay, paper number 1.
It's wet.
Wow.
Paper number 2. Message.
Happy fall break.
Yeah.
Whoa, dude.
Oh, wait a minute.
You're pulling a quick one on us. What the?
Bye.
There goes our happy fall break.
That's not what it meant.
There goes our fall break, yeah, there goes our fall break, guys.
Now you can drink water.
How many spot fishes do I get if I
No, we should drink it.
That looks tasty.
So really quickly, you don't have to write this one down. I'll do another demo next time. But what could we claim about the IMFs of that paper? They're blue. They must be similar to the water because the water was able to get in there and break it up. I don't know if this is true, but I once heard that whenever they have a very secure piece of paper, they sometimes will use like government. They'll like use this so they can like, instead of shredding it, like.
Does that paper burn easily too?
I don't know.
Actually,
I've never tried
that was a confidential, like, piece of paper.
Thank you guys. Have an awesome fall break.
My family's leaving me for Dallas. I was supposed to go to Dallas and with them for a baseball game, but I forgot to take out work. Like I heard a lot.
Yeah, so she's like, what I am.
I mean, I'm gonna be at home comfy, you know? Yeah.
Is this on?
I don't want to imagine that, but okay.
See, I didn't kill you this time.
Like, London, that will have your body. Pretty much.